You are most welcome to the second lesson of work, power and energy. In our first lesson, we looked at work, but we can go back and review what we had discussed. We defined the work as the product of force and the distance moved in the direction of force. We saw that work is measured in joules, whereby we defined a joule as the work done by a force of 1 Newton to move a body through a distance of 1 meter. Still, from the definition of work, we looked at the formula for finding the work done. That was force times the distance. But when is work said to be done? Work is said to be done when the point of application of force moves in the direction of force. That is when work is done. For instance, if you apply force on a table to make it move and it does not move in the direction of the force, that means that there is no work done. So work is only done when you apply force on a body and it moves in the direction of the force. We can look at solving problems involving work. From the formula of work, which is force times distance, we can work out problems. In our examples, number 1 says a force of 10 newtons moves a body along a straight path and stops after 200 joules of work has been done. They want us to find the distance that was moved. For us to find the distance, we must first of all know what work was done and the force that was applied. We are lucky enough given this in the question. We are given the force and we are given the work. But remember, work equals to force times distance, meaning that distance equals to work divided by force. So the work of 200 joules is divided by force of 10 newtons to get the distance moved, which is 20 meters. In our second example, we are told that a tangential force of 15 newtons is applied to turn a wheel of radius 70 centimeters about the center. They want us to find how much work is done in 2 revolutions. So in this question, we are given the force, the radius of the wheel, and the number of revolutions that were made. So from the radius of the wheel and the number of revolutions, we shall get the distance moved. How do we get this? We know that the distance moved around a circle is given by its circumference. but the 2 revolutions means that that circumference was moved twice. So to get the distance, we shall multiply the 2 revolutions by the circumference of the circle, thus giving us 4 pi times the 70 centimeters are changed to meters to give us 0.70. That is the distance that was moved, and the force is 15. So we multiply the 15 times the distance to give us the work that was done. Example 3 says that a body of mass 5 kilograms is released vertically at a height of 80 meters. They want us to find how much work is done. So you see that the example 3 is a bit different because we are talking about vertical motion. So for vertical motion, the force is equivalent to the weight of the body. So that is mg, and the work done is given by the force times the height raised through. That's why we are getting work done as the weight of the body times the height raised, which gives us 400 joules as the work that was done. After looking at work, let us look at power. Power is defined as the rate of doing work, meaning for you to get power, you are going to divide the work you have done by the time you have taken to do that work. Power is measured in watts, and since we have said that power equals to work over the time taken, therefore it means that 1 watt equals to 1 joule of work per second. And therefore from this we get a definition of a watt, which is the rate of doing work of 1 joule in 1 second, or the rate of doing work at 1 joule per second. Examples, we are told that a pump delivers water at a rate of 1 liter per hour to a tank that is 20 meters above a well. We are supposed to find the power of the pump. So if you look at the question, we are given the capacity, that is 1 liter, we are given the time, that is 1 hour, and we are given the height, which is 20 meters. So for us to find the power, we must get the work done over time taken. But work done, since it is raised, so it will be the weight that is raised per hour times the height. But weight, for us to find the weight, we must find mass. Don't forget, from density equals to mass over volume, that's where we shall get our mass as density times volume. But the 1 liter is capacity. However, 1 liter equals to 1,000 cubic centimeters. So if 1 liter is equivalent to 1,000 cubic centimeters, and we know the density of water, which is 1000 kilogram per meter cubed or 1 gram per cubic centimeter. So using the volume and the density, we can get the mass, and that mass is 1 kilogram. So after getting 1 kilogram, to get the weight, we shall multiply the 1 kilogram by 10, which gives us 10 newtons, and to get work done, we multiply the 10 newtons times the height, which is 20 meters, which gives us 200 joules. And to get power, we divide the 200 joules by 3600 seconds, which are equivalent to 1 hour, to give us the power as 0.556 watts. So what we need to know about power is, 1, we must know the definition of power. We must know the formula for finding power. We also must know the SI units of power. Sometimes we are given power in kilojoules or kilowatts, sorry. If we have power in kilowatts, kilo means 1000. So that means that 1 kilowatt equals to 1000 watts. Sometimes we are even given this in megawatts or gigawatts. Megawatts, that is 1 million watts, and so on. Let us look at energy. We are defining energy as the capacity or ability to do work. And just like work, energy is also measured in joules. We go to forms of energy. We have various forms of energy, which include the following. We have mechanical energy, which is the combination of kinetic and potential energy. We have mechanical energy. We have chemical, heat, light, sound, nuclear. We have electrostatic. We have other many forms of energy. But after knowing these forms of energy, then we come to their sources. Where do we get these forms from? These sources are categorized into two. We have the renewable sources and the non-renewable sources of energy. To start with the renewable, these are sources that are readily available. For instance, the sun. From the sun we get solar energy, which is converted to other useful forms, because the solar can be converted to electrical, which is also converted to light, heat, among others. Then we have wind as another renewable source of energy. From wind, the wind can be used to run the windmills, which are connected to generators that generate electrical energy. We have the geothermal. We have the hydro, that is running water. So those are the renewable. Renewable are non-exhaustive. They cannot get exhausted, and these are free of charge. No one will charge you for collecting solar energy from the sun. No one will charge you for using the wind to run the windmills that generate energy. No one will charge you if you have a waterfall and use it to generate the hydropower. Then we have the second category, which is the non-renewable sources of energy. And the non-renewable, since they cannot be renewable, are exhaustive, meaning they can get used up. Some of these are oils, like the crude oils where we get the petroleum and so on. We have the gases, like the biogas. We have coal, we have charcoal, among others. These ones are non-renewable, or they are exhaustive, or they get used up, and since they get used up, they are rare, expensive, but again they are readily available. Okay, we shall look at the forms of energy in details one by one. So we shall start with mechanical energy, which is defined as the energy possessed by a body due to movement and location. And this is made up of two parts: the potential energy, which is possessed due to its position, and the kinetic energy, which is possessed due to the virtue of its motion. Potential energy is equal to the work done in raising a body to that position above the reference level. So for a body to gain potential energy, it must be raised above a certain reference level, and it is that work done in raising this body that is equal to the potential energy. The body is capable of doing work which is equal to the potential energy, and if it returns to the reference level, then that body of mass m at a height h above the reference level has a potential energy that is equal to mgh, where m is the mass, g is the acceleration due to gravity, and h is the height above the reference level. To discuss more about potential energy is further subdivided into other categories. For instance, we have the elastic potential energy that is found in elastic materials. We have the electrostatic potential energy, which is between charges at rest. Then we have the gravitational potential energy. So those are the categories of potential energy. Let us go to kinetic energy. Kinetic energy is defined as the energy possessed by a body by virtue of its motion. So this means that a body can only possess kinetic energy if it is in motion. For instance, if we consider a body of mass m moving at a speed v and has kinetic energy that is equal to a half mvh, where m is the mass and v is the speed. So if a body is moving from rest to a certain velocity v, or speed v, then the kinetic energy it has is equivalent to the work done by the external agent that makes it acquire that velocity. For instance, when you kick a ball which is currently stationary, the ball moves with a certain speed, but the kinetic energy of this ball is equivalent to the work done by the force you apply on this ball to make it acquire that velocity. We have examples. Number 1 says an object of mass 3 kilograms is moving at a speed of 5 meters per second, and if it is to be stopped in 5 seconds using a uniform force, they want us to find the power which is supposed to do so. Remember, we saw how we get power. Power equals to work done over the time taken to do that work. So meaning that we must find the work done. We are already given time in the question. We have mass and speed, but the work done to stop this object is equivalent to its kinetic energy, and therefore that work done is equal to a half mvh, which gives us 37.5 joules. Then to get power, we divide this by 5, and we shall have our power as 7.5 watts. In example 2, we are told that in the previous example, that is 1, suppose the stopping force acted over a distance of 4 meters. What was the force? Suppose this stopping force acted over a period of 4 meters. Then, what was this force? Remember, from the formula for work done, which is force times distance, we now divide the work done by distance to get the force. But we have already got the work done, which is equivalent to kinetic energy, and we are given the distance, so we shall be able to find the force. In example 3, we are told that a man of mass 75 kilograms walks up 12 steps, each 20 centimeters high, in 5 seconds. We are supposed to find the work he developed, the power he develops. So for us to find the power he develops, we must first find the work done by this man, and we divide this work done by the time he takes to find his power. Work done equals to the weight of this man times the total height he moves or risen. But the total height, remember, he's moving on staircases which has steps, 12 steps, but each of 20 centimeters. So to get the total distance or the total height, we shall get the 12 steps times the height for each, but we change that to meters. So it is 12 times 0.2, which gives us the total height that this man went through, and we multiply that by his weight to get the work done. Then we divide the work done by the time taken to get the power he develops. So that has been work power. We are still moving with energy. We shall look at the principle of conservation of energy. The principle states that energy is neither created nor destroyed, but can be changed from one form to another. In other words, in an enclosed system, the total energy is always constant. This can be evidenced using the simple pendulum, among other experiments. So we shall look at the interchange of energy in the gravitational field. A body moving under the influence of gravity possesses constant mechanical energy made up of two parts, that is kinetic if it is moving and potential when it stops moving, which is equal to mechanical energy, and it is constant. So it is now the transformation between the two. When the body starts moving, the potential changes to kinetic. When it stops, the kinetic changes back to potential. So that's what we call the principle of conservation of energy. We cannot create, neither destroy, but we can transform from one form to another. Just like you transform electrical energy to light, or electrical to heat, or mechanical to electrical, and so on. So that implies that the kinetic energy lost is equivalent to the potential energy gained. At the highest point, the particle has no kinetic energy, but maximum potential energy. And on falling, it keeps on gaining the kinetic energy, but at the expense of potential energy. When you throw a ball, it goes up, but it goes on decreasing its kinetic energy, because as the ball goes up, its speed goes on decreasing. And remember, kinetic energy depends on the speed. So it reaches the maximum point where the speed is 0, and at that point it has maximum potential energy. Then as it is coming down, the potential energy goes on changing to kinetic, because the speed is increasing. As the speed is increasing, kinetic energy is also increasing, but at the expense of potential. Let us look at the simple pendulum. If we consider the simple pendulum, a mass freely suspended on a string forms a simple pendulum. And when this mass is pulled to one side and then released, it swings between two extreme points, that is A and C. But at these extreme points, it's where it has maximum kinetic energy, and it has maximum potential energy and 0 kinetic energy. At those two extreme points, that is at A and C. Because at those 2 points, the mass is momentarily at rest, and therefore its velocity v is 0. So it has maximum potential energy and 0 kinetic energy. But at point B, this mass has maximum kinetic energy and zero potential energy. So from this observation, it implies that since the mechanical energy is conserved, it cannot be lost, then the pendulum would swing forever with a constant amplitude. It could not stop swinging because the mechanical energy is conserved. However, if you try that practically, it is not the case. Why? It is because of two reasons. One, it is air resistance and friction. So the energy is lost in trying to counter the air resistance and the friction at the point of support. That's why the amplitude keeps on decreasing until it is zero, then it stops swinging. But if it wasn't the air resistance and the friction, then that means that it could keep on swinging forever. And this idea can be exhibited in what we call the pendulum clocks. Search about the pendulum clocks.